Hello everyone. So in here we want to presentation. We need to introduce ourselves. Start from me, Abiyan Azis with student ID 24151010057. And my friend.
Introduced, my name is Kadek Arya Darma Pradnyana with 3 digit ID is 063.
And my name is Almasrazqi Suwatno with student ID 2415101055.
So from the first, I want to represent about reflection operator. The reflection operator is a linear transformation that maps its vector to its image or reflection with respect to a line in R2 or a plane in R3 which passes through the origin 00 or 000. This is flips the position of the vector to the other side of the line or plane by the same distance from the line or plane. Represent that reflection on R2. From the first reflection about the x-axis, the pattern is t equals to ty equals to t minus y, and the standard matrix represent as 1, 0, 0, minus 1. And for the second reflection about the y-axis, txy equals to minus x and y. And the standard matrix represent as minus 1, 0, and 0, 1. And for the third reflection about the line y equals to x, where the t, x, y equals to y x and represent in standard metric as 0, 1, 1, 0. And now we came to the reflection on R3. On this table 2 reflection about the xy plane, t x y z equals to x y minus z. And in standard matrix equals to 100, 010, minus 1. And the second reflection about the xz plane, t xyz equals to x minus yz. And in standard matrix, 100, 1, 0, minus 1, 0, 0, 1. And the third reflection about the yz plane, txyz equals to minus xyz. And in standard matrix, minus 1, 0, 0, 0, 1, 0, 0, 0, 1. And now we come to the standard reflection matrix for the R2 and for the R3. A1 equals to 1, 0, and A2 equals to 0, 1. And then for the R3, A1 equals to 100, and A2 equals to 010, and A3 equals to 001. And from the first, calculate the shadow for each standard matrix using transformation rules. As we can see that the result into standard matrix column as T A1 equals to V1, and then for the T A2 equals to V2 and T A3 equals to V3. And then the standard matrix represent as in standard matrix A equals to V1, V2, and V3. And for the exercise, I use the second question multiplication to find the reflection of A, B about the A x-axis and B y-axis, and then C line y equals to x, and the x-axis which have pattern x y equals to x minus y, and we multiply the AB into the x-axis using reflection operator, and as we can see that the result means A minus b. And then for the second y-axis, t equals to xy equals to minus y, and multiply by the y-axis pattern from the AB, and as a result in minus AB. And then the last line y equals to x, which is t xy equals to yx, xy equals to x, and multiply by AB, and then the result mean that BA. And now we come to the projection operator, linear transformation that maps its vector to its image on the line in R2 or built in R3, orthogonal or perpendicularly. And from the table 3, this means the projection in R2. This means from the first operator, orthogonal projection onto the x-axis with pattern that Txy equals to x0, and in standard matrix so that 1 0 1 0 0 0, and on the y-axis Txy equals to 0y, and in the standard matrix represent as 0 0 0 1, and then the standard projection matrix for R2 in R2 represent in A1 equals to 1 0, A2 equals to 0 1, and then we transform into transformation matrix and equals to the standard matrix as Ta1, Ta2, and for A3, A1 until A3, and then represent in the standard matrix as Ta1, and then Ta2, and then A3. Now, in the exercise 4.9 on the question number 7, use matrix multiplication to find the orthogonal projection of -2, 1, 3 onto the xy plane, and then xz plane, and then yz plane. And as an answer in xy plane represent as -2 and then 1 0, and for the xz plane represent as a result in -2 0 3, and for the yz plane result as 0 1 3. This means that the projection for orthogonal of vector -2 1 3 to the coordinate of three plane can be done using the projection matrix from the table 4. The result xy plane and xz plane and yz plane. And for the next will be represented by my friend Arya Darma. Take your time.
First, I will present about the question 3 in table 5. A rotation operation in R2 is a linear transformation that rotates every vector combination counterclockwise about the origin through an angle theta. Jadi vektor di R2 adalah transformasi yang dirotasikan vektor berawanan arah jarum jam dengan sudut tertentu with an defined angle. It's called theta. To construct the standard metric of the rotation, we use fundamental idea from section 1.8. In this table 5, we can see in this illustration, there's a matrix X and Y rotated counterclockwise with a new vector value called W1 and W2. There's rotated counterclockwise with this theta value. Vector X and vector Y. Vector X yang dirotasikan dengan nilai tertentu mendapatkan vektor. We can look this rotation equation. Y W1 equals X cos theta minus Y sin theta. W2 equals to X sin theta plus Y cos theta. In this standard matrix, we change Y value into column vector. We got cos theta minus sin theta, and cos theta. Next, before that, I will explain the table 6. The table 6 is the vector in R3, rotation vector in R3. You can see the operator counterclockwise rotation about the positive x-axis through an angle theta. The rotation base rotasinya itu berada pada sumbu X, pusatnya ada di sumbu X. Rotation equation W2 is Y cos theta minus Z sin theta. W3 is Y sin theta plus Z cos theta. In the standard metric form, we got 1 0 0 0 cos theta minus sin theta 0 sin theta and cos theta. Jadi sebuah benda dirotasikan terhadap sumbu X akan menghasilkan matriks yang seperti ini. Second operator is counterclockwise rotation about the positive y-axis through an angle theta. Jadi sebuah bangun ruang dirotasikan terhadap sumbu Y. In this y-axis, we got W1 equal to X cos theta plus Z sin theta. In W2 equals to Y. In W3 equals to minus x sin theta plus z cos theta. The standard metric form is cos theta 0 sin theta 0 1 0 minus sin theta 0 and cos theta. Counterclockwise in third operator is counterclockwise rotation about the positive z axis through an angle theta. So the bangun ruangnya dirotasikan terhadap sumbu z. In this rotation, we got the rotation equation W1 equals to x cos theta minus y sin theta. W2 is x sin theta plus y cos theta. In W3, we got equal to z. The standard matrix form in this z-axis is cos theta minus sin theta 0, sin theta, cos theta, and 0, 0, 0, 1. Here's the standard matrix of these three operations. In this R3, I will move into the exercise with pair 45, the vector 3 minus 4 multiply with this value. We multiply as usual, root 2 over 2 times with 7 and minus 1. That will equal, we change the form into row matrix, row vector 7 per 2 root 2 and minus 1 per 2 root 2. And this is the rotated matrix or vector. This is the result of exercise number 3. We will next into number 4. Alright, the question number 4. A dilation or expansion is a transformation that scales all coordinates by the same non-negative scalar k. So the vector is applied by a scalar value that always positive, non-negative scalar. Called the scalar value is k, construction with vector k in R2. This table is in R2. When 0 less equal to k less than 1, a vector is times with scalar k would expand that more bigger than the original vector. Setelah dikalikan, vektornya akan tambah membesar. Dikalikan dengan scalar k, maka vektornya akan bertambah besar. The same with second relation with vector k in R2. When k is bigger than 1, that would be coordinates. When k is bigger than 1, example 2, 3 or more than that, the k will bigger than example number 1. So you can see in this effect on the unit square, the square is more bigger than the first square. Perbedaannya terlihat jelas pada contoh nomor 1, ketika nilai k kurang dari 1, antara 0 atau 1, antara 0 dan 1 maksudnya, maka ukuran perseginya tidak sebesar yang nomor 2. Ketika K lebih dari 1, maka perseginya lebih besar dari nilai yang antara 0 dan 1. The standard matrix form is like this, K0, 0, and K. This is the 4 vector in space, in 2-dimensional space. These two vector are the same with standard matrix. Okay, next page, please. Next page. Okay, the table 8, in this 3-dimensional space, we can see the operator construction with vector k in R3 when 0 equals less than equals k less than 1. This is also maybe similar, little similar with 2-dimensional vector. Maybe the square would less than the k bigger than 1. Jadi ukuran vektor dari nilai k antara 0 dan 1, dia lebih kecil dari ukuran k lebih dari 1. We can see the standard matrix form is k0, 0, 0, k0, and 0, 0, k. Maybe in this 3-dimensional matrix, there's z is involved here, different than 2-dimensional matrix. Okay. Danvi, please stop the canvas screen, and Abiyan share the whiteboard, please. We use, for example, a equals to, we change the value of k become this. After that, we computing the value of this vector a minus 1 and 2 multiply with the scalar matrix 1 over 2 times minus 1 plus 0 times 2, 0 times minus 1 plus 1 over 2 times 2. And the result is minus 1 over 2 and 1. And this is the result. We change the column into row form, minus 1 over 2 and 1. And yes, this is it. This is the exercise. We solving one exercise. Here's my explanation. The next explanation will be held by my friend. Okay. Abiyan, stop the whiteboard share. And next to Danvi explanation. Thank you.
Okay, so now I will explain about expansion and compression in matrix transformation. Before we start to look for the table, I will define expansion and compression. So expansion and compression are linear transformation that change the size of an object into two-dimensional space. The transformation works by multiplying one coordinate of a point by a non-negative vector k. This operation doesn't alter the object overall. Instead, it enlarges or shrinks the object along a specific axis, or horizontal or vertical. The value of k determines the type of information. As we can see in the operator column, if k is more than 1, it means it is an expansion. The object stretches in the specified direction because points move away from the axis. And if k is more than 0 and less than 1, it will be compression. The object shrinks as point move close to the axis. And if k equals to 1, it means that no change occurs. The object remains the same. So this transformation preserves straight lines because they are linear. So let's take a look on the table. Start from transformation along the x direction. We can see from the illustration here, t x point y equals to scalar k multiplied by x point y. What does it mean? First, only the x coordinate change. Only the x coordinate change, and the x and the y coordinate remains the same. When k is less than 1, the object becomes narrower horizontally. As we can see in the illustration here, the k is less than 1, the object will be narrower horizontally. And then if k is more than 1, like in the second row, the object will become wider. And for transformation along the x direction, have a standard matrix of k, 0, and 0, 1. Let's get to the transformation along the y dimension, along the y direction. As you can see at the illustration, tx point y equals to x point k multiplied by y. What does it mean? It means only the y direction or the y coordinate that changes, and the x coordinate remains the same. And then when k is when k is less than 1, the object will become shorter but vertically, as we can see in the effect on the unit square from the third. And then when k is more than 1, the object will become taller, as we seen in the effect of the unit square, that in the fourth row it is taller because the k is more than 1. And then every point will move closer to or farther from the x-axis depending on k. So transformation along the y direction have a standard matrix of 1, 0, 0, k. And how to obtain the standard matrix? There are 3 steps that we can do to get the standard matrix. First, we will take the standard basis of E1 equals to 1, 0, and E2 equals to 0, 1. And then we compute the image of each basis vector. As you can see in the third step, there is arrange these images as the column of the matrix. So as we can see in the slides, in the example of expansion or compression in the x direction, there is 2x point y equals to scalar k x point y. Since we know that t e1 equals to k0 and t for e2 equals to 0, 1, we will make it as a matrix. So the standard basis will be k0 and 0, 1 in vector form or in matrix form. It is will be the same for y direction. And then there is an example of problem or exercise that I get in the 17th number. Use matrix multiplication to find the compression of minus 1.2 in the x direction with vector equals to a half. So first of all, we will substitute the k into the formula or standard basis of compression transformation in the x direction, which means it is k0, 0, 1. Because we substitute the vector k into the compression formula. So it will be like this, vector 1 per 2, 0, 0, 1. And then in the question, there is we have to find the compression of minus 1.2 or coordinate minus 1.2. So we have the vector here. It is minus 1, 2. So when we just have to multiplicate it with the basis vector that already substituted by vector k. Then there is a and vector u. We multiplied it. And after we multiplied it, we will have the result will be the compression of coordinate minus 1.2 in the x direction with scalar k equals to 1.2, 1 per 2. And then there's example of matrix transformation of expansion in the x direction with the factor of k. Now, so before, I mean in the 17th number or 17th question, there is the k is less than 1. It is 1 per 2, which means 0.5. But in the 18th question, the factor k will be more than 1, which is it is 3. So first of all, like before, we define the standard basis, and then substitute the factor k into the formula of or basis vector of expansion. And after that, we multiplied the factor a with the factor u that already exists in the question. After we get the result of the multiplication of the factor multiplication, we will get the result of the compression of coordinate minus 1.2 in the x direction with k equal to 3. Now I will explain about shear. Shear is a linear transformation that shifts or slides a point proportionally to uh, one of its coordinates. This means that that the position of the point changes diagonally, but one axis remains unchanged. Shear doesn't change its shape into a parallelogram. And now I will explain shear in the x direction. So as we can see in the operator, tx point y equals to x plus k multiplied by y point y. And that is the formula for shear in x direction. What does it mean? It means points are shifted horizontally, and then the amount of shift equals to k multiplied by y. And then the farther a point is from the x-axis, or we can say that it will be larger. And longer the shift. And then points on the x-axis or y equals to 0 will make doesn't move. As we can see in the effect of the unit square, when the y is 0, it doesn't move. And then we will talk about the effect of the unit square. As we can see, the unit square becomes a parallelogram. As I said before, when the y is 0, it will stay and remain unchanged. And when 0, 1 moves to k1, the vertical side becomes slanted. And then the area stays the same, but the shape becomes slanted. And then there's a shear in the y direction by a factor k, especially in R2. So the txy will be x point y plus k multiplied by x. What does it mean? It means the shift occurs vertically. And then it will means the amount of shift, and then points on the y-axis. If the x equals to 0, it will be doesn't move. It's like the inverse of the y equals to 0 before. And how do we find the standard matrix? Here's the standard matrix, and how do we find it? As simple as we define the standard matrix in E1 equals to 1, 0, and E2 equals to 0, 1, and then we compute or we substitute in the transformation formula that txy before. So this is how we get the transformation or standard basis. Let's get back to the effect of the unit square. What does it mean? Effect on this unit square. First, 0, 1 moved upward to 1k. It is the middle unit square. And then the horizontal slide becomes slanted, and the squares become a vertically shared parallelogram. So shear is a simple linear transformation that slants a shape without changing its area. It is implemented by adding a multiple of one coordinate to the other, which means it will give a matrix with a single of diagonal entry. So this is an example of the, what does it means? Example of problem or exercise. We'll take the 21st number. So they are given a matrix, and I will try to identify the shear transformation. So the answer of this problem is the shear information will be at A3 and A4. Why? Because matrices A3 and A4 is the shear information because in the A3 the matrix matches the form of a vertical shear. Let's see again. This is the vertical shear, which means it is shear in the y direction by factor of k in R2. And A3 matches with that with factor k. Factor k equals to 1/2. And it will shift the point vertically parallel to the y-axis, where the displacement is proportionally to the x-coordinate. And A4 is also matches the form of vertical shear with K2 equals to -1/2. It is the vertical shear in the opposite direction compared to A3. So I think that's all presentation and explanation from us for the assignment of linear algebra and many of basic metrics in transformation. So I think that's all from us. Thank you for your attention and see ya.